Dear friends, now we will see an example number 22 of exercise. The question shows that a geostationary satellite orbits the Earth at a height of nearly 36000 kilometer from the surface of Earth. That means a satellite is above 36,000 kilometer from the surface of Earth. What is the potential due to Earth's gravity at the site of this satellite? Now we have to find out the potential. So we have already a very known equation that V is equals to minus G me upon Re plus H. Now if we go with this equation, we have already the well-known terms that here we can say that in place of G we can put 6.67 into 10 raised to minus 11. Mass of Earth that we know, that is 6 into 10 to the power 24 kilogram. Then radius of Earth, that is about 6400 kilometer, that we can write, that is 6.4 into 10 to the power 6 meter, and plus the height is given, that is 36,000 kilometer, that is 3.6 or a 36 into 10 to the power 6 meter. So all these are given value. When we simplify this, we can have a very simple term, and the answer, that is minus 9.4 into 10 to the power 6 joule per coulomb. So joule per kilogram. So this is the potential of the site where the satellite is. So this is your example number 22. It's very simple question. Now we will move further and we see the example number 23. So in this example number 23, we are given very good information that a star which is 2.5 times the mass of the sun and collapsed to a size of the 12 kilometer rotates with a speed of 1.5 revolution per second. That means it is extremely compact star of this kind are known as a neutron stars. Certain observed stellar objects called pulsars are believed to belong to this category. Now, will an object placed on its equator remains stuck to its surface due to gravity? Here mass of the sun that we have to remember is 2 into 10 to the power 30 kilogram, and here the mass of this star is 2.5 times of it. So now first of all we can say that the object will remain stuck to the surface of the star due to the gravity if the acceleration due to gravity is more than the centrifugal acceleration due to its rotation. So now we find it, that acceleration due to gravity. So first of all we say that G is equals to G, then capital M, that is the mass of star, and R square, that is a given distance for the 12 kilometer. So here we can replace all the values. We can give G as a 6.67 into 10 raised to minus 11. Then mass is given 2.5 times the sun, so 2.5 into 2 into 10 raised to 30 kilogram. Then R is given 12 kilometer, so it is 12,000 meter and its square. So this answer would be, that is 2.3 into 10 to the power 12 meter per second square. So this is the gravitational acceleration. Now we find centrifugal acceleration. So we say that centrifugal acceleration, a centrifugal we say CF, that is r omega square. Now obviously it can be written as r 2 pi f square. Now here we can say that this value is given as 1.5. It is there written that certain obstacles tellers with a speed of 1.5 revolution per second. So it is given, that is r is 12,000 meter, because it is given as a 12 kilometer, then 2 into 3.14 into the value of f, that is 1.5 revolution per second, that is a frequency, that is 1.5 whole square. So this answer comes to be 1.1 into 10 to the power 6 meter per second square. So here it is very clear that gravitational acceleration is more than the centrifugal acceleration, and therefore we can say that the body will remain struck with the surface of star, as we can simply say, therefore G is greater than ACF, and therefore it will remain struck to the given surface. So this is example number 23. Now example number 24. 24 example gives the information is like, in example number 24 it is given that a spaceship is stationed on Mars. How much energy must be expended on the spaceship to rocket it out the solar system? Mass of the spaceship is given as a 1000 kilogram. Mass of the sun is 2 into 10 to the power 30 kilogram. Mass of the Mars is 6.4 into 10 to the power 23 kilogram, and radius of Mars is 3395 kilometer. Now radius of orbit of Mars is given, that is 2.28 into 10 to the power 11 meters, and capital G is given as a well-known equation. So first of all we calculate the total energy of spaceship. Here we consider that the radius of the orbit of Mars be r, and r dash be the radius of itself, that is Mars. M be the mass of the sun and m dash be the mass of the Mars. So here we put all these things, that is radius of orbit of Mars is given, that is 2.28 into 10 raised to 11 meter. So here we say that r is 2.28 into 10 raised to 11 meters, while r dash is given, that is the radius of Mars, that is 3395 into 10 raised to 3 meters. In the same way, mass m is the mass of sun, that is given 2 into 10 to the power 30 kilogram, while m dash, that is given that be the mass of Mars, and mass of Mars is given 6.4 into 10 raised to 23 kilogram. Now another thing that we can have, the total energy of spaceship can be determined. Total energy of spaceship, that can be written as minus g m m over r minus g m dash m over r dash. Here another thing, that m, that is small m, is a mass of spaceship itself, that is given 1000 kilogram. So m is 1000 kilogram, that is mass of a spaceship. Now from this equation we can say that energy required to rocket out of the spaceship from the solar system is equals to minus of total energy of spaceship. So total energy required, total energy required to out the spaceship is minus of total energy of spaceship. That is called the total energy of spaceship. So from solar system, so this is the first thing that we can put, that is equals to plus g m m over r plus g m dash m over r dash. Now we just simplify all the terms. When we simplify all the values, that is g small m, that means m over r plus m dash over r dash. When we put all these value together, we can have the equation value as 5.98 into 10 to the power 11 joules of energy. So this would be the total energy in the terms, and that is ultimately the completion of your chapter number 8.
Exercise also, it is also very clear example. We have already done this type of example earlier. That is 25 number example gives us the information that is very peculiar. What it gives us that a rocket is fired vertically from the surface of Mars of which is 2 kilometer per second. If 20% initial kinetic energy is lost due to the atmospheric resistance, how far will the rocket from the surface of Mars before returning to now the mass of Mars, as we have discussed, and the radius of Mars is also given earlier, and G is also having the Bernoulli notation.
So here we say that small m be the mass of rocket. So small m, that is mass of rocket, and it is of, say, moving in a particular direction. Then capital M, be the mass of Mars, that is 6.4 into 10 to the power 23 kilograms. Then we can also consider r, that is the radius of Mars, that is a radius of Mars, that is equals to 3395 into 10 to the power 3 meter. And suppose V is given, that is 2 into 10 to the power 3 meters per second, that is the velocity of the rocket. So now initial kinetic energy is 1/2 mv square, out of only 20 percentage, and 20 percentage of it's loose due to Martian atmospheric resistance. So we can say that that is 1/2 m v square into 20 percentage of it, that is lost, so remaining only 80 percentage, that is the total energy. So kinetic energy will be 80 percentage of its original. Then potential energy, that is minus g m m over r. And obviously when it reaches the maximum distance, so in a first condition we can have total energy in condition 1 is equals to kinetic energy 1 plus potential energy 1. We can give here the name kinetic energy 1, this we give name as a potential energy 1. So this is your total energy 1. Now at far away, so when it reaches, when rocket reaches the maximum height, then say h, then kinetic energy 2 will become 0 and potential energy 2 will be minus g m m over r plus h. So this will be its total energy at that time. So we can say that total energy 2 is equals to kinetic energy 2 plus potential energy 2. Now we can compare these equations, that is equation 1 and equation 2. So from equation 1 and 2 we can say, that is from 1 and 2 we can compare this equation and write that 0.4 mv square is equals minus g m m over r is equals to minus g m m over r plus h. So we can have the simplified term for the height. We can say, if we bring this equation to the right hand side, we can have the term, that is G M M over R plus H is equals to G M M over R minus 0.4 mv square. This m will cancel out from each term. Now if we simplify the term, that is remaining term over here, we can have Gm over R plus H minus Gm over R is equals to minus 0.4 v square. Now we simplify Gm R minus H upon R into R plus H is equals to minus 0.4 v square. Now we simplify this. Here we cancel out this R, and therefore minus H Gm over R into R plus H is equals to minus 0.4 v square. Minus term will cancel out and we can get 0.4 v square into R plus H upon G into M. Here we can take this H upon R plus H as a term to simplify the value. Here this will be 0.4 v square R over Gm. Now here we can put it as, separating the term, we can have the value, if we reverse it, that is R plus H over H is equals to Gm over 0.4 v square R. Again we can simplify it by keeping in a manner, that is R over H plus 1 is equals to Gm over 0.4 v square into R, and therefore R upon H is equals to 1 minus, here it would be Gm over 0.4 1 upon v square into R minus 1. So if we simplify this value, we have, that is the equation that we required, and we can have that H is equals to, that is 495 kilometer in the range. So this is the answer from the example number 25.